Hello.
So yeah, hello, hi everyone. So I'm audible, right?
Yes, sir. You're audible.
Okay. So today we'll discuss regarding the seventh week, I guess, right? So sixth week, that graded assignment submission date has been passed, right?
Yes, sir. It's been passed.
So what's the deadline for the
15.
next week?
22. Like, it's a 22.
20. Okay, 22.
22nd.
Okay. So have you went through the content? Like how many of you have went through the content? Because I don't think there's much, like only 3 or 4 lectures are there. Out of those 4 lecture, I guess in 2 lectures or as only described the data set, I guess. Some data has been described in the one lecture. So I think so there are only 2 or 3 yeah. So yeah, Ganga Prasad. You can go ahead. You have raised your hand, right?
No, I have gone through the content. That's what you were asking, no? That's what.
Yeah. Okay. So okay. So only one guy has went through the content. Any other? So nobody else has.
Most of them must have gone through that, sir. Most of them must have gone through that. Yes, yes.
Okay. So whoever has gone, can you raise your hand?
Yes,
I
yes,
can know regarding the audience.
Yes, yes,
Okay.
people are very-
3
There are-
people. Okay. Okay, then I'll just go through the content once more. Like I'll just go through the slides. But somebody, okay, you only asked on the, I guess, discourse regarding the data set and all, right, Ganga?
Yeah,
Yeah, so
today
only
today I posted. Yeah.
okay.
So what I requested, okay, that's good that you have gone through that post. So
Yeah,
what I
I
said
just
that
went through the post. I
correct.
just
So as you rightly said that the number of videos are less, but it's a complete, it's a one kind of jump. Like from probability, now we are moving into the real kind of statistics. As in one of your live lecture, you had also said that real statistics will start from week 7, right? You had said this.
yeah.
Yeah,
So
correct. So now sampling theory and also so many terms have been used. It appears that mathematics part is bit easy, but if you take an example with the help of Excel, then that
yeah,
will
I'll
bring
just
more
tell you
clarity.
with some example, but I don't have the data set. But
So
I can tell
we
you with
can
some.
generate, na sir, we can generate any kind of data. Like let us take the packaging of milk filling, milk pouch. So
Yeah, yeah,
one lakh
yeah.
packets
That
have
is
been
what I'm
produced.
saying. That is
Correct.
what I'm saying. I'll tell you with some random data set.
Yes,
Okay.
it's random data. I'm not saying that the real life data, random data, so that the concepts are clear. When we are talking about
There are
sample, we are
only, I
talking.
guess, 5-6 term that has been. See, earlier week 7 was having like it was too heavy. I guess earlier when I used to take the last term when
Now
I
I
went.
think it has been distributed into week 7 and week 8 now.
Yeah, I guess because when I was going through the slides today, so it was not like the all the rest, but like the most of the MGF and all has been moved to, I guess, 8th week.
Yes,
So
sir.
now you're having only 2 or 3 lectures. So we'll just go through that. If you have like, if any of you will be having any issue in the technical, like the
one
board
one
or
one part of MGF has been discussed in week 7 also. So you can explain MGF also, no problem in that. One part of MGF has been discussed in week 7.
okay. So okay, but that is the that like it's not mandatory for, I guess, if somebody is going through that, then if you are asking, I'll explain you. Otherwise, we'll just restrict our lectures today till like whatever the content we are having in the segment. And if you're having doubt, you can just stop me and ask. Okay. I'll just share
May
my
I make a request, sir, first?
yeah.
Sir, it would be great, sir, if you just kindly, if you just mention briefly the topics that are covered in week 7.
That's what
Just the name of the topic, sir. That would be great.
Okay, so I have that formula sheet that was there in the portal. Okay, with that on the same formula sheet, I'll tell you which are the topics that has
No,
been
sir.
discussed.
No, sir. It's not about formula, sir. So it's about the
Not
content.
formula, not formula. I'm telling in the formula sheet itself. I'll tell you what are the topics that has been discussed, or I'll just go through the I guess the slides that has been used in the lectures. Okay,
Yes, sir. That, yeah,
that
sir. I really
that will
appreciate,
be
sir.
fine, right?
Thank you. Yeah.
Thank you, sir. Just before you start the slide, just if you can give me the give us the topic names. That will be excellent, sir.
There's like in week 7, I guess only 3 topics has been discussed. Not much has been discussed. Like simple stuff has started with like you have to calculate. Okay, I'll just share the screen first. Yeah, so out of 4 videos, one is related to data. So that is the I guess third video, right? Okay.
Good evening, sir.
Yeah. So we'll start with the first lecture. I guess in the first lecture, uh, just about first lecture, the professor has just talked about. The first point is if you're having some sort of like if you're having a data set, like you have got some small samples of data set, okay, and you don't know about anything, you don't have any idea about the population data set, right? For example, some normal distribution you are having, okay, and out of that normal, so you are having some bigger normal distribution, and out of that normal distribution, like you have taken out some samples, like you have done some sampling, like 10 times you have done some sampling from that distribution, whatever you've been having in the starting, okay. So when you are doing that sampling, like you have taken out 5, 10 samples, like you were having starting a distribution, okay, and out of that distribution you have in the first sampling, like for example in the first sampling you have taken out some 10 samples, okay. Similarly you did for n number of times, like 5 times you did, so 5 times you did the sampling. So I'll tell you all the words first, okay. So what are the words that has been used in the lectures? So the first thing is the sampling should not create any like confusion. Sampling means if you're having a bigger distribution or the parent distribution, okay, like for example say any distribution, and out of that distribution you are taking out the samples, okay, n number of times. So now you did n sampling, okay. N sampling is like first in the first sampling you taken out the 10 samples, smaller samples you have taken out of that from the bigger distribution or the parent distribution, okay. So in the first, this is the first, that wherever you're having the capital X1, that generally represents everywhere the first sampling that you did. Okay. Similarly, x2, if somewhere is there, it's the second sampling. Okay. And if you have been, and in the first sampling, like for example, I've taken out 10 samples. This is the first sampling. Okay. Karthike, you want to ask something?
No, sorry, sir. I just raised by mistake.
Oh, okay. Okay. It's fine. Who is this Bhaskar? Okay, Bhaskar. Okay, it's fine. So I don't know. Maybe it's not correct. So what I was telling, we are having some parent distribution. Okay, and wherever you are having this capital X1, X2, X3. Okay, so capital X1, X2, X3 generally represents the number of sampling you are doing. Okay, number of sampling means you are taking. So for example, at 5 o'clock in the morning, you taken out some 10 samples. Again, after 2-3 hours, you did the sampling. Okay, you taken out 10 samples, right, at 10 o'clock. So the sampling I did it in this morning 5 o'clock, that was the first sampling I did. And in that sampling, I taken out 10 like 10 samples out of that parent distribution. And again at 10 o'clock in the like morning after 5 hours from the first sampling, I did again the sampling. So at that time, again, I took out some 10 samples out of the like whatever the parent distribution I was having. Okay. So the first thing is pretty simple. This wherever you are having this capital X1 generally represents the the sampling number. Okay, this is the sampling number, and the instance that you are taking out in that sampling is the simple samples. Okay, so if for example in the X1 capital X1 I have some 10 samples, so whatever the samples can be anything, right? It depends upon the distribution you're having. So that will represent you the simple samples. Okay, so like for example, in this first sampling, I taken out some n samples. So this generally the samples will be simply represented by x1, smaller x1, x2, x3, x4. Okay, so many times like everybody will tell the same, like for the capital X1 also the sample, and for the smaller x1 also the sample. So don't get confused with those. Like the way that generally people say same, like the samples only for everything, because this is the also a type of samples only that
So
I take
what is small x1, sir? What is small x1, x2?
like for example, I'm having some bigger distribution, right?
Yes.
So there is some distribution. Okay, like for example,
That is
some
a population.
that is population. Okay.
Okay.
And out of that population, like for example, now I just did first sampling, and in that first sampling, I taken out some 10 samples from that parent distribution. Okay, so this is that 10 samples.
Okay. Okay.
In that first sampling, I taken out 10 samples, right? So again, after 5 hours, I did the sampling x2, that is the x2. Okay, and I taken out some 10 sample again. So those again, that x1 till x10 will represent the samples corresponding to the second sampling. Did you like? Is it fine? Like,
Yes, yes. Okay.
it's clear, right?
Sir, what you mean to say is that out of the population, say at a 5 a.m., I go and pick up 10 people, 10 random people. Is that what you're saying? And then at this is my first sampling, and then at another time period of time, I go and do my second sampling, which consists of again taking up 10 random people.
Yeah.
Is that what you're
So
saying?
that is fine. This is also, this is correct. I am just giving you the reference to understand the time difference.
But
I can
then
do the sampling
what
at
does
the same
X1
time.
mean for the, say, for instance, if I take up 10 random people, then there must be X must represent some values, like either it's male or female, or like if they are left-handed or right-handed. Is that something like that?
Which one?
Like
This X1.
What does small x1, small x2 mean?
X1 represents some numerical value. Like for example, see, this is a normal distribution I am having. Okay. Okay. Some sample I've taken out, like this sample I've taken out. So this value would be there, right? Some value, for example, 0.5. So x1 equals to 0.5. This I taken out. These are samples, right?
It could be a weight, it could be a height, it could be something like
Yeah.
Yes.
It can be anything, right?
Okay. But just as a quick question, can this be Bernoulli also?
Yeah.
or is it like always normal?
No, can be anything. I'm telling you, just
Okay.
for example, this one. The
Okay,
parent
got-
thing can be anything. So
Got you,
you will
sir. Right.
see in the future that everything will generally get converged to a normal distribution. Okay, even if you are having Bernoulli and you are doing the Bernoulli for n number, like very large number of times, for those cases also it will get converged to normal distribution. Maybe in the next week itself. Okay, that is fine. So yeah,
Sir, sir,
yeah.
yes, here itself for simplification, that is the reason why I was asking, like, can we take an example, like say for example, as Anirban was saying, that can be weight or height, right? Anything.
Hmm.
So
Hmm.
can we take a hypothetical examples for say, for example, like a
Like for example,
biscuit packet. So my population is 1 lakh packet, right? Of 100 gram biscuit packet. So now I am taking a first sample of 10 biscuit packet, right? So this way can we interpret like first sample contains 10
okay. So
biscuit
you are
packet.
having what you are having a packet of biscuit packet, right?
Yeah, 100 gram biscuit packet. Yes.
Okay, that 100 gram that biscuit. Okay, I'll tell you. Okay, this is a simple distribution where the rate of that 100 gram biscuit packet varies.
Yeah,
Okay, so that can be of this.
mean is 100 grams, so it can be 98, 99, 100, 102, like that.
Okay, so see, one thing is what you are fixing. You are fixing weight, right? And the rate you are varying.
No, I am not fixing. I am asking for clarification. Can we understand to this way? I'm just asking. Can,
So
can I interpret it like this? Let's say, for example, when I'm taking X1 sample and there are 10 pieces, so there are 10 packets, right? So that one packet is X1, the other packet is small x2, the other packet is small x3. Can I say like this? That's what I'm asking.
you can say, but you're not able to tell me what are the things that you are wearing. Like for example, this is a distribution where I'm telling this is the weight of the person of the weight of the population of the people, where the weight is varying from some value. Like this is the mean, like this would be the mean weight. Like for example, the mean weight of the Indian population would be around 65 kg. Okay, and that is varying from like for example 40 kg to 100 kg,
Okay.
right?
Okay.
What is the thing that is varying for you? Like,
So
for the biscuit packet, maybe the rate of
no, let us
ऐसे कर देगा तो सर सर वैसे कर देगा तो
please mute him, sir.
yeah.
अरे पागल कहीं का पागल लाइसेंस का ही सब लगा रहा है
Okay, so it's fine.
Yes, sir. So let us take the example of humans only, right? So I have picked up 100 men, right?
100 male.
Sorry, 10. The first sample is 10 people, right? So can I say that?
Yeah, so in the first sampling, you took out the weight of 10 peoples, right?
Yes. So the X1
Okay,
is
so this is the first sampling.
No, there are 10 people in this sample, right?
Okay, so yeah, so in the first sampling you took, so this doesn't have the 10 people. This will be having this is a population distribution, right?
They can
So
be
this should be having a bigger
people.
number.
Yeah, 1 lakh people may be there.
Yeah, so what are the data you have like from the like for example, you collected the data from some 60K peoples. Okay, and then you have plotted some graph. This is the parent distribution you are having. And now from that parent distribution, now you are taking out 10 peoples, the weight of 10 peoples, right? In the first sampling. This is what you are saying. Correct?
Yes, I'm asking. Yes.
Yeah.
Is the interpretation correct or wrong?
Yeah, it's totally correct.
Okay. Thank you.
Okay. So whatever the thing, like you are out of this 1 lakh people, you are taking out the 10 outcome, like 10 samples in the first sampling. Okay. So you'll not take out from the same instance, right? Like you'll not take out the same value 10 times. Because in the random sampling, whenever you do the random sampling, you'll take out the value randomly, right? You'll not take out the same thing again and again, right? So that's why whenever like there was a question also, okay, is this a random, like whether the thing that the sample mean, whatever you'll get is a random or not? Because every time you are taking out the 10 people's, okay, weight, so the mean value would be not same every time. Like for example, in the first sampling, the mean value can be around 60K. In the second sampling, you'll see that the mean is like 63 kg. In the third sampling, it can be 61 kg. So every time the mean value is getting different, right? It can be same, but it can't be also. Okay, so it can vary. But the most important thing is whenever you'll start increasing the number of samples, if you are in the first sampling, like for example, I taken out some 10,000 people's samples, right? now you will see that the mean, whatever you're having, the sample mean will start converging to the population mean. Are you getting my point? So when I will start increasing the number of samples in any sampling, so the value of mean, the sample mean will start converging to the population mean. Is it fine? Is it fine or what? You slept?
So can you repeat it once again, please?
So what I told, whenever you increase, like in the first sampling, like this was the data set, like this was the distribution I was having. This is the normal, like simple distribution I'm telling. I'm not going anywhere in IID and all. So I'm just telling you the simple basic thing. So if I'm having this distribution, the weight of the person of the whatever the data I have calculated from 1 lakh people in our country. Okay. I just took out some in the first sampling. I took out the 5 people, like 10 people's data, like the 10 weight of the 10 peoples, and I calculated the sample mean. Like the sample mean is what? This is simply in the first sampling I take out the weight of the 10 peoples and then calculated the mean of those weight, and I get to know this is a 60 kg. Okay. For the second sampling, I took out the 10 peoples again and I saw this is a 63 kg. Okay. So this was a bit closer to the population mean, but it was not more. Like if you'll start increasing the number of samples in any sampling, like for example, in the first sampling, I took out some 10 peoples, right? Now I'll take out some 100 peoples. Now you'll see that whatever the mean value you are getting now, this time it would be a bit closer to the population mean. This is what I'm saying. And now if you'll start increasing more number of samples in any sampling, like for example, now I took out 10k people weight and then I'll calculate the mean. You'll see that this the mean value now, whatever you're getting, it would be a bit more closer to the population. Okay, is it fine?
Yes, we understood, sir.
Yeah, yes,
Oh,
sir.
okay.
Yes, sir. Yes, sir.
How many times, like how many samplings we'll do? Is that that, for example, like 10 or 20, or how many times we will do?
Okay, how many times? That means the number of sampling you are asking.
Yes. That will be given. Is it?
Okay. In the question, if somebody is asking, I don't, they'll ask, they'll give you everything, right?
Yeah. Okay.
Yeah. Okay. So
Sir, is the number of sampling is related to the mean will be close to the population data set, like number of sampling or the samples?
Number of samples in any sampling generally will tell you the
like here
close.
you take 10 people. If you will take 100 people, it will be close to the population data set.
Yeah, correct.
Mean of the population. Okay.
Yeah. Because the sampling is not making any impact, right? The sampling generally, the number of sampling we are doing, what we are doing simply. I just took one example, like I'm doing the first sampling now, and after 1 hour I'll do the second sampling. That is not going to help me in like giving me the correct.
Then what is the benefit of doing sampling here? Like any particular benefit?
सर
Yeah.
सर ये जो 2 वर्ड बोल रहे हैं आप, सैम्पलिंग और सैंपल, तो सैम्पलिंग हो गया x1 x2 जो यहाँ है, और सैंपल मतलब हाँ कैपिटल x1 और जो सैंपल का मतलब जो 10 हमने लिया 10s वो सैंपल हो.
हाँ.
Thank you.
Okay. Or sampling, why we are doing more? See, for example, this is the one simple example I do. Like for example, in the first sampling, just for example, I'm telling you, in the first sampling, I just took all the datas, all the samples, whatever I took. It's a random thing, right? Like for example, I just use the Python code to take out the 10 random values. And for example, that Python works in such a way that it took out all the samples between this and this, below that mean value, all the values, whatever in the first sampling. Okay. So only one sampling will also not help us to give us the correct sort of mean, right? If like, for example, this is the, all the data, whatever we have taken out in the first sampling has came from this data set. Okay. So in this case, the mean value will become very less, right? It would be around 45 kg, right? And again, if we'll do the sampling more and more number of times, it will help us to know regarding the mean value. Okay, in these cases. In other cases, like in the IID, like in the Bernoulli, that we will discuss in the, so that will help us to know regarding the probability steps also. Like for example, so in the Bernoulli or in the, whenever we'll change that Bernoulli in some indicator form. Okay, so in that, in those cases, we'll be having only 0, 1, 0, 1 cases, right? Like for example, in the first sampling, I did the first sampling and I got, like for example, out of 10, I got only 3, 1, right? So there the probability will become 3 upon 10. But if we'll do that sampling more and more number of times, that will help us to know the exact probability value, right? So the sampling also generally help us, will help in some or other way, right? Did you get the point now? A bit
Yes, sir. Yes, sir.
more clarified, right? So till now, if you are having any issue, you can ask. So this is clear, like what is sampling and what is sample, right?
Yes, sir.
Yeah. Okay, so I'll just go through the slides now. So in the first lecture, sir has talked about the Bernoulli trial, Monte Carlo simulation, and computing the histogram. This, if we'll go through the lectures also, I don't think so that there is much to discuss in this, the first lecture. The Bernoulli trial, you already know what is the Bernoulli trial. Monte Carlo simulation, I guess you already have done some work there. And histogram and all. So this is the basic stuffs in the first lecture. There's not any conceptual thing in the first lecture. Okay, wherever it's there, I'll just discuss this. So the Bernoulli, already the experiment and the event of interest A, occurrence of the event A is considered success and not success. You can calculate the probability as 1 minus probability of A. Okay. Okay, so IID, you already know that. So if we are having this, see, like I was having this Bernoulli samples, like this is the samples, for example. Okay. So yeah, so this, okay, so if we are having indicator, you already know, if I'm having some Bernoulli trial, I can change that into indicator. Indicator generally means, and any other cases also can be changed into indicator. That means if you are just putting the random variable x equals to 1, that means the occurrence of or the success of that thing. Like for example, I'm just throwing a dice, okay, and if I'll in the indicator, I just want to keep, whenever I'm getting 6 as a success and the rest other cases as a failure, then I'll just put whenever x equals to 6, I'll get 1, and other than all the cases will get 0. That the probability of the success will be 1 upon 6 and the failure will be 5 upon 6. Okay, so anything can be changed, like not anything, but most of the cases can be changed in the form of indicator. And what is so wherever you are having doubt, you can ask in between also, because what I feel is the first lecture, there's not much to discuss anything. Okay.
So may I ask a question regarding this first lecture?
Yeah,
so in the first lecture, what was coming up for me, like how I got it, was that ultimately, like when we are collecting samples, or if we draw a histogram or draw a frequency table, so ultimately the frequency table will give me the probability. Like if I divide the frequency table by the number of occurrences or the number of observations, that will give me the probability only.
Okay, probability. Yeah, from that smaller sample, you can get the probability also. Yeah.
Yeah, that's what I got.
Yeah. So all the basic stuffs, like in the histogram, like for example, you have to estimate probability between A and B. Okay, so you'll count the number of success between A and B, and will divide upon the number of thing or the number of beans that you are keeping between A and B. Okay, so you'll get a bit like the probable, because it's not the exact thing, because you are calculating for some samples, right? So this will not be exact same as the population mean, but this will be a bit closer, or you can say not almost, but a bit you can get an idea regarding the population mean also.
So then, what is Monte Carlo simulation actually? Like, it is only the finding the frequency, finding the frequency of the success. Like here, we are changing sample size from 10, 100,000, and then finding the
probability.
Probability,
So
or you can say that is only Monte Carlo simulation.
Yeah. So you can apply it for the tosses. You can see that if 500 random samples you are doing, what's the probability you are getting of the success of head or tail. So you'll see that whenever you'll start increasing the number of that random thing, that will start converge to. Yeah. So this is what I think you did in some extra activity thing also, right? So from the second lecture, there is thing to be discussed. Okay. So where is that second lecture will start? Like for example, here the same thing I told you. I'm having 20 IID Bernoulli with probability P. So in the next upcoming lecture, you'll see that if I'm not knowing much about the population, like population, what you can say, the curve or the population sample, like the data set, then also in the future upcoming thing, like we'll be able to at least know regarding the mean, variance, sample means, sample variance, or like for example, I have a normal distribution, like normal distribution generally have the two parameters. So there will be some basic parameter, like normal distribution generally have two parameters, right? The variance or the mean. So if you have been given only the samples, okay, not the exact same population curve, like not the same population, what you can say, the data set. So you are having only the sample, because most of the time you'll be having the samples only, the small number of samples. And from that samples, you have to use some method, like we'll be discussing, like the maximum likelihood or some other method to know regarding the, if you're having this mean and variance of the normal sample distribution, you can guess, not guess, but some mathematical interpretation will be able to know regarding something about the population also. Okay. So, but this is the starting point of that. So like, for example, here we are having 20 IID Bernoulli P samples with P is unknown. So what I did in the first sample, when I took out, like I was having some distribution, and out of that, this in the first sampling, I took out this in the first sampling, I got the samples as this. Okay. So with this samples, I can know regarding the P. That P won't be same as this Bernoulli P, whatever from where we are taking out the samples, but we can get the idea, right? Every time the sample 2 or the sample 3, whatever the sample number of samples you are doing, every time the sample mean would be different. Can be same sometimes, because if for example, because number of 1, you can get 10 out of 20, or you can get 11. So other time, like in the sampling, like for example, in the first sample you got 11 the success, or in the next, again in the 11th sampling you are doing, you got the number of like success as 11 only. So sometimes you can get the same sampling, the sample mean, but not the every time. That's why this is the random variable. The sample mean itself is a random variable in the sampling that you are doing.
Sir?
Yeah.
Just a small clarification, like these 20. So these 20 are called by samples, right?
Which this one?
Yeah, this 21, 1, 0.
Yeah. These are samples.
And these are independent and identically distributed, right?
Yeah. This is identical and independent also. See, why identical and independent?
So suppose there are three samplings, sampling 1, sampling 2, and sampling 3. So I suppose these are also IID.
Yeah, this one.
Sampling 1, sampling 2, sampling 3. So they are also IID.
How come this be IID? See, how come if I'm doing some sampling for the first time, and again I'm doing for the second time?
Yes.
It's not related at all, right?
Okay.
Because we are doing in some different, like for example, I told you one example. I'm doing it now, and again I'm doing it after 1 hour.
No, why I'm asking, just let me give you perspective. We are calculating mean from each sampling, right?
Yeah.
And you're saying that mean is also a random variable, right?
Yeah.
So this question is obvious to come into mind, whether these random variables, whatever I am getting as a mean, so whether they are among themselves identically distributed and independent or not. So from that perspective, I am asking this question.
Like for example, you did sampling 20 times.
Yes.
So
and I get 20 different means.
Yeah, 20, you can get 20 different mean or 15 different mean.
Yes.
Okay, right? So every time you are getting a bit different random variables. Okay,
Yes.
so that's why it's a random. That is why we are saying it's a random.
So
Now, what's your question?
What kind of relation they are sharing among themselves? What kind of relation are? Do they share any kind of relation? Like when we say independent and identically distribution, it means they are independent of each other, right?
Yeah, they are not the first sampling or the whatever the samples I'm taking out. That is not getting influenced. Like for example, in the cricket, okay. So whenever it's not exact correct, but I'm just telling you a brief. Like if you need, like for example, if in the cricket, like for example, if the batsman need some 20 runs out of 6 ball, okay, but that won't be similar. Whatever the data, like for example, I told you the number of runs that has been scored out of 1 ball can resemble the dice system, right? I'll tell you, like for example, the batsman can score 1, 2, 3, 4, even 5 also he can score. So he can score 1, 2, 3, 4, 5, 6. Anything he can score out of 1 ball. So if some player has came for the like in the starting, like just he came for the he's playing for the first ball, okay, and if some the same player playing in like whenever he needs like 20 or 25 runs out of 6 balls, those cases can't be compared, right? Did you get something, or should I try with some other example?
Okay, let me put my question again. In sampling 1, I am getting a mean, right? In sampling 2, I am getting a mean. In sampling 3, I am getting a mean, right?
Yeah.
All of them are random variables.
Yeah.
So my question is, can we say anything about these 3 random variables, like whether they are independent of each other, they are identically?
Yeah, they are totally independent of each other.
And they are identical.
They doesn't depend upon each other. Yeah, they are identical, and they are identical means you should not assume that this identical as a if I'm getting the same value to the, like I am getting the first mean as 0.5 and second mean again as 0.5, that means it's become identical. That is not identical. The numerical value is same, but it's not like it's totally dependent, like independent of each other.
Okay.
Right? In the first sampling, it was totally different. The second sampling is totally different. The third sampling is totally different. Only the data, like only the common thing is the distribution, the population distribution from where we are taking out. But the thing, whatever we are doing, is totally independent of each other. That's why, yeah. Okay, so this is what I was saying, like for example, model of samples. So this is the typical or statistical problem. So wherever you are having the C, capital X1, X2, X3, all if I was like, for example, X was the starting point or the parent distribution. Okay, so the parent distribution was having some PMF, okay, PX. So X1, X2, X3, whatever the sampling we are doing will also resemble the same. Okay, so that the samples in the first sampling or the samples in the second sampling, that will also resembles the same PMF. Why? Because see, I told you whenever I'll start increasing the number of samples in any sampling, that will start converging to the value of expected or the population mean. Why it is converging to the population mean? Because the distribution, whatever I'm having for the population, will start, like the population of the samples will also start resembling to the population. That's why we'll start getting the same value as the sample mean equals to population mean. Well, we'll start increasing the number of n to very large. Okay, so that's why it's written like if X is the PMF of some this, then the each X or the sampling will also resemble almost the same population density function. Okay, and Xi are important, that we already all the sampling are independent from each other. That's not dependent on any of the other samples, on any of the other samplings and all. And the data small x1, small x2, x or from the one sampling instant. Like for example, this all can come from x1 also. This can come from x2 also, or xn also. Okay. So this mostly in the statistical problem, what we are trying to solve, that will look maybe in the next week. if I'm having some distribution that I know the distribution, okay, it's a normal distribution, but I don't know the value of the parameter. Okay. So how will you know that parameter? Only I'm having a simple samples value. Like for example, I have only 20 or 50 samples from that bigger parent distribution. Okay. And I need to know regarding the parameter of those bigger parent distribution. Okay. So there are some estimation method that we'll work on to know the parameter of the bigger estimation or the parent estimation, or the, you can say, the population density, population distribution. Okay. So this is what I guess sir has told to find information about the distribution. Okay. So the goal, our goal is to procedure to find the information regarding the distribution of X. X here represents the population density, population distribution. Okay. Till now it's clear, right? So I guess the samples for the data set, for the population density, population distribution, sample distribution, sample mean and all. This is clear, right? So now I'll move to the second lecture. So if you're having doubt, you can ask. I'll just wait for some 10 seconds.
Sir, can you scroll up a bit back to a couple of slides?
Yeah.
One more. Yeah, this one, sir. The one you scrolled past.
Yeah.
The next one, sir, please. The next one, sir, please.
Okay.
Yeah, this one. So basically, what this particular slide, what I'm getting, what's coming up to me is that, like, if I want to go to say school or somewhere, and I want to find out what is the ratio of boys versus girls, and I'm just talking from a Bernoulli distribution, and I pick up a random student. I call up a roll number, and a random student comes, and I check if it's a boy or a girl, and I know it's going to be a Bernoulli distribution, right? But I don't know what is the parameter P, the probability of finding a boy or the probability of finding a girl.
Okay. Yeah.
Is this what it's trying to say?
Yeah.
Okay. And so the other thing is that, sir, like you mentioned, x1, x2, xn could come from x1. Can you just repeat that part? You just, you wrote with blue arrows.
Okay. So this X is the population distribution. Population means the parent thing, like the parent distribution, the bigger distribution from where we are taking out the sampling. We are doing the sampling. Okay.
So come again, sir. So come again, this X, right? This is a population distribution, you can say, right?
Yeah, this is the population distribution.
Yeah,
and from that population.
Yeah, we can say, so we can say like that. You mean to say like, okay, suppose you have 100 students, okay? So this X can be the mean of 100 students if you take in one sample, okay? If you take 100 people in the one sample, so this will be average. It will be very close to the population one, right?
Repeat it.
Okay.
If I'm having this X,
if you have 100 people, 100
already I'm having only 100 people in the population. Yeah. This is what you're saying.
If you increase the sample size to the close to the population, okay, that is nothing but 100. Correct. Yeah. So if you take their distribution, okay, I mean, if you take out the mean or like whatever the measurement you are doing, so it will be same to the population.
It will start converging. Like if you increase and like
I take 10 samples, I take 20 samples, and then I 30, 50, I go close to the 100 samples, sir. Okay.
But the thing is, but if you are taking out the 100 samples also, there is no guarantee that you're taking all the samples only one time.
Exactly, sir. So actually, my question actually is not about
start converging toward the population mean.
Yes,
it will not be exact.
Yeah,
this is what I'm saying.
Yeah. So actually, my doubt, I think the guy who has asked the question, I think you can go ahead with that thing. Okay. After that, can you take this doubt? I just want to know what is this x1, x2, sir. I know this is a random variable. Okay.
This x1.
Yeah, this x1, x2. Yes, I have this thing.
Okay.
Because I think you have taken this is the you can say a mean or like average of one particular sample, right?
This is not the mean.
Yeah. Any. I mean, your whatever.
I told you. Okay. In one example, I told you. So I'm having the data. I collected the data from some 1 lakh people of India. I just asked regarding the weight. Okay. This is a basic example just to tell you what is x1, x2, x3. So I got So some people would be will be having weight something like 40 kg. That I'm assuming this is the minimum weight that Indian people generally have, and that can go till 110, right? And the mean weight, what do you assume? Like it should be around 65 or 60 kg, right?
Correct, sir.
So there will be this type of plot. Correct. So this is our population distribution. Like I collected a very
This is you can say say mean. Can't we say as a mean, sir, for time being?
Yeah, this is the mean 65
kg. Average or like whatever mean.
The population, right? Mean, the exact mean of the population.
This is a mean of one particular sample, right, sir? Isn't it, sir?
This is not for the one sample. This is the parent distribution. This is the X, capital X.
Okay, yeah, this is capital X, sir. This is capital X.
Yeah,
suppose this 1 lakh people, if I distribute into 10,000 each sample, sir, each batch.
Okay, so now you are having some infinite number, like this 1 lakh people. That for us 1 lakh is the infinity.
Correct, sir.
Just for I assume that. And now I'm taking out some sample, the first sampling. In first sampling, what are the number you want to take out? Like
well, for example, 1,000 or 10,000 is okay. 10,000. Okay.
10K people.
Correct.
You are taking out 10K. Like this is one, this is second, third, fourth. Similarly, you taking out 10K weight from this population distribution. Okay.
Correct,
so and then if you are able to calculate, like for example, you will get some x1 value, small. Like for example, this x1 was 41 kg. So you just randomly took out one in the first sampling. Like I'm doing it now. Like at 8 o'clock, I'm doing the first sampling. I just taken out this value, and this was like 41 kg for me. And then again, I take out the second sample, and this was like 64 kg for me. So similarly, I taken out 10,000. You are telling. So 10,000 I took out. So these are the first sampling I was doing. And the 10,000, I just divided with the 10,000. I got some mean value.
Yeah.
Right?
So you again got the mean of that sample, right?
This is the sample mean of this sampling. Okay.
Yeah.
Yeah. This is the sample mean. Again, if you want to do this resampling after some 1 hour, or two people are doing the sampling at the same
second
time.
Sample. You can say second sample, sir.
Yeah, this is the second sample. This is not second. This sample, second sampling, and out of this many times everything gets like every time I'll say maybe from the next week I'll say for the X2 also samples, X1 also samples. So don't get confused with that. Like X2 is the second sampling, and in that second sampling, I just took out again 10,000 people's weight and divided with the 10,000 to get the second sample mean. This is first mean.
Yes, you got the mean of that also. Correct.
Yeah. Okay. So if I'll start increasing the number of n, okay. So I'll next time I did the sampling, and there I took out 50,000 people's samples. Okay. So when I'll take out the 50,000 people in some sampling, like sampling number 3, I took out some 50K people's weight. So that mean will get more closer to the population mean. That's 65.
Yes.
Okay.
Sir. Yes, sir.
Yeah. So this is what we are discussing. Is it clear?
So here my one question, sir. I'm sorry to taking long time.
Yeah,
so in this set, sir, okay, the X1, X2, the set, okay. So should we keep every time the sampling number of people same, or like it can vary also, sir? Okay.
So you can vary also that sample. Maybe in the lectures we have just taken out the same numbers every time. But if in the normal scenario, if you see, you can vary the number of samples in any sampling also. That is why if you want to get a bit closer to the mean value, if you want to predict something, right? So you need some more number of sample data, right? So this is what, so in the third sampling, in the 2 sampling, we did with the same number of data set, like 10,000 we taken out. But I need some more clarity, or what you can say, the more predictable mean value. So what I did, I took out some more number of data sets from that, whatever the population density, like distribution I was having.
Yes.
There I'll be more, what you can say, more confident, or more, I'll be having more confident to say, this is the sample mean, and where I took 50K data set will be more closer to the population mean of the, like in this case, in the X3 sampling, I'll be getting some value around 64.8. So there I can say this is a bit more closer to the whatever the exact data or the exact population mean I'll be having. Yeah.
Correct. Understood, sir, this thing.
Sir, I have a question, sir.
Yeah.
Sir, related to the sample mean and the population mean. So in population mean, we divide by n. And in sample mean, when we take sample mean, we divide by n minus 1.
Okay, in the
Sir, is there any
variance. you are
logic
asking.
or?
In the variance, right?
Yeah, sir. Yeah.
So in the variance, somewhere some books generally takes n, some book generally takes n minus 1. What I think
Okay.
that can be wrong. The what method they're using, I don't know. But what happened? See, when I was going through some blogs, so in one that can be wrong. Okay, so I'm telling in the starting itself. So what he started doing, he was having some bigger population distribution, and then he was doing some uh, sampling he was doing. And when he was doing the sampling, he was calculating the variance every time. And when it's a simple hit and trial method he was doing, and when he started doing with the n, so that was not much closer. And when he started doing the n minus 1 plus, and the reason he gave was whenever you'll be having one value for one value every time, that value was coming 0. And I guess for the mean value, uh, uh, I think, I don't know, I am forgetting the thing what he told, but he told some one for one value, it was coming every time 0. So he started taking n minus 1, and then n minus 1 starting popular. But I'm not sure whether it's the correct or wrong. If somebody of you are knowing about that, you can tell. Otherwise, like, we have to just Google that why n minus 1 is chosen. But some books also take n also. That is also correct.
Okay, so the both way it is right.
Yeah, both ways right, but here you have to choose n minus 1.
in IIT.
Yeah, because you can get wrong answers, right? So it's better to choose n minus 1 if you have been asked to calculate the sample values. So till now it's clear, or anything more you need to clarify? Okay, so I'll just move to the second lecture. Okay, the second one is the empirical distribution. This is like let x1 till xn belongs to some, it's from some parent distribution or population distribution via IID. Like, it's all the sampling, whatever we are doing, is independent of each other. Okay, and then xi denotes to t denotes the number of times t occurs in the sample. The empirical distribution is the discrete. So this is pretty simple. Okay, so you just have to count the number of success and failure out of whatever the number of sampling, whatever the number of samples you took out. Like, for example, here n was equals to 20, and out of that n, so whatever the number, so we can count and then we can calculate the basic probability. So this is simple. Okay, so one thing. Okay, so till here it's here also it will be a random thing. So you'll be having issue in sample mean, calculation of sample mean, and then the sample variance of the mean. Okay, so can somebody tell me why, if somebody has seen the lecture, so if you are having some sample mean, you can calculate directly. Okay, so you did some, like, for example, in the first sampling you got some n samples, you can calculate the sample mean simply. Why that variance is sigma square upon n? What is the physical significance of that? Why? And what's the difference between this sample mean, sample variance of the mean equals to sigma square by n? But if you will calculate the sample variance, that will be similar to that will get converged to the sigma square itself. So what's the difference between those two?
Sir, can you please repeat the question?
Okay, so you did one sampling, right? So you got some sample mean. Okay, so the expected value of that sample mean will be almost similar to the variance, not variance, the population mean. The sample variance of that mean, why it is sigma square by upon n, and the sample variance of any district or any sample, like if you did one sampling, and the sample variance of those samples, why it is same as sigma square. But in the case, if you are calculating the sample variance of the mean of that samples is coming to be sigma square upon A. So I'll tell this is the correct. So if we are calculating the sample variance, this is the sample variance. Why this is sigma square upon A? And if you calculate the sample variance only, sigma square. What's the difference between these two?
Average of this one and variance is sigma square, sir. And whereas sigma square by n is average of sample.
What sigma?
Sigma square is the variance, whereas sigma square by n is average variance.
Yeah.
Variance of average.
Okay. So, okay, I'll tell you. So till now the descriptive variance. Okay. So this X bar generally represents the sample mean. If for the one sample, if you have done some sampling, one sampling you did, and then you have calculated some sample mean, this is what X bar or the smaller X bar represents the sample mean. And then you will go through the sample variance. Where is that sample variance here? So sample variance is the second lecture itself, right? So this all are like pretty simple. The same thing has been discussed again and again.
Sir, what was that small X bar that scrolled by?
Where this one small X bar is the sample mean. So this is a way of representation. See, capital X1 generally doesn't represent anything. Like capital X1 is just it doesn't have any intuition with the maths. Capital X1 is simply the sampling I'm doing. This first sampling, this is capital X1. Okay, so a small one only represents the samples, or anything that is represented mathematically is the small X1. Okay, so capital X1 doesn't have any mathematical, it's just telling you it's the first sampling I'm doing. That's it.
I mean, like for instance, if we go back to that example of collecting the heights or the weights from a random population, am I audible? Right.
Yeah,
so,
you're audible.
So for my first, like my X1 would mean what? X1 would mean my first sample. Like I go to the first guy and his weight. Let's say I'm collecting weight. So X1 would be say 45 kg. X2 would be say 54.2 kg. XN should be X10 should be something around 70 kg, right? And then I divided that, sum it up, divided by 10, and I get my X bar, which is the mean of my first sampling. I get a figure, right?
Yeah, so it's totally correct. And again, if you are doing the second sampling and then you will do the same thing and again, you'll get the sample mean of the second sampling.
I get that.
Yeah.
But the problem is I'm unable to reconcile what does small X bar here mean.
X bar is what you have calculated, right? X bar, what you calculated for the first sampling. Okay. For the first sampling, you calculate a sample mean. This is what X bar is.
Oh, okay. X bar will be for X1, we have an X bar. X2, we have an X bar. So like that only. Got it.
Yeah.
Thank you.
So again, these are all examples only. Like there, it's a Bernoulli 0.5 samples. Okay, so the sampling you did for the first time, you are having 5 samples. The sample mean is what? 3.5. So this is the same thing we are doing again and again. So here also the Bernoulli of 0.5. Here also the same sample. So Bernoulli 0.5 generally represents a bigger, or you can say the cloud or the parent distribution. And out of that parent distribution, I'm taking out some n sampling I'm doing. Okay, and all these are ID with 0. Only 0 or 1 can be possible with probability 1/2, because the parent distribution was having the probability that is 0.5. Maybe in the upcoming video, you'll not be knowing regarding the P, that you have to predict with some estimation, like with some random things, like some samples you'll be given, and then from that random samples you have to know or estimate the value of the population mean. Okay, so in the upcoming things, that is the like the statistical estimation that we'll be doing. So with the help, you'll not be given this value. You'll be given only P, and you'll be given some samples of some sampling. Like you did one sampling and you got some sample value. Out of that samples, you have to, with some mathematical intuition, you have to say regarding the population mean or population probability of Bernoulli or whatever the distribution has been given. Like for example, if it's a normal distribution, you'll be having mean and variance. Okay, so you'll be given some sample values, and from that sample values you can use some Bayesian estimation or some estimation like maximum likelihood estimation to know regarding the nu or sigma. Okay, so
Sir,
this is, yeah.
could you explain those two terms, like expected value of sample mean and variance of sample mean? Could you explain
Expected value of
sample mean and variance of sample means?
Yeah, this is what I'll explain. I'm just going through the same thing. I'm just searching for where that sample variance has been taught. So till now, sample mean has been taught, right?
So just to reconfirm my understanding.
Yeah.
Like when I'm saying sampling one, right?
Yeah.
Here you can write. So I'm taking 10 samples, right?
So you are taking, this is a simple distribution for your
yeah, just want to reconfirm my understanding. So for sampling, I'm doing sampling one. So you can write sampling one.
Okay.
And I'm taking 10 samples.
Okay.
So I'm adding them up and dividing by 10. So I'm getting this corresponds to mean of my sampling one. Am I right?
Yeah. This is the sample mean of your first sample.
First sample. Simply, since I've got the mean, going by our stats one method, we can also calculate the variance also, like x minus x bar summation and divided by n.
What?
So that will become variance of my this particular sampling one, right?
So okay. So now you have got, see, one thing again. So you have got x1 bar, and if you want to calculate the variance directly, you can calculate, because you have mean, you have these samples. Now you can forget the sampling and all, so you'll get the sample variance, right? Okay. Yeah, so this you will get the sample variance. But one thing, if you have to get the sample variance of the mean, sample variance of the mean is different thing.
So
if
so could you explain that terminology? What is meant by that? Sampling variance of the mean?
So sample mean of the variance is different, right? So that you generally calculate.
Is that does it mean the variance of all the sample means or what?
Okay. So sample sample variance is simple thing. You got the point. Sample mean is simple thing. You got the point. These are all for the one sampling, right? The sample variance, the sample variance of mean is simply sigma square upon n. If you just think, if you will start increasing the number of samples, okay, what will happen to this? This will start decreasing, right? Overall, the sample
will start reducing. Yes,
it will start reducing with 1 upon x. Okay, why it is happening? Whenever you will start increasing the number of samples, what will do? It will start having the variance. So this is variance, right? So the variance will start decreasing. Okay, the variance will start decreasing means the spreadness of the data will start decreasing. The spreadness of the data, and I'm calculating for the mean only. So the spreadness of the mean will start decreasing. Okay, that means you'll start getting the mean value. If you'll start increasing the n, it will start increasing the value of n. The sample variance will start decreasing. That means you'll start getting the value, the sample mean, as population mean. Did you get my point? The variance will start decreasing. If the variance is start decreasing, that means the fluctuation, the variance, when the variance is larger, when you are having the values which are very much like, apart from the spreadness of the data is very high, like the values is very apart from the mean value. If if you are getting all the values as the mean value only, there the variance will be 0 because there is no spreadness of the data. All the data are mean only. So when you will start increasing the value of n, that means the spreadness is getting reduced. Spreadness is getting reduced means the variance, the mean value or the data set, whatever you're having, is almost closer to the mean value. See, this is the example. This is the basic normal distribution. Okay. So if the variance will be smaller, that means what? This will start going like this, right? If the mean variance will start decreasing more, it will go like this, right? Because all the value will start converging to the mean value. This is what here. If we'll start increasing the n, sample mean related to the sample variance of that mean will start decreasing. If we'll increase the n, and that means the value of the sample mean will start going converges toward the population mean.
Sir, can you explain this thing by an example?
Okay, I'll just go through the slide, the same slide where the professor has described. Okay, so these are the earlier we were talking about the Bernoulli here, the normal distribution, just the samples, and then calculate the sample mean. So see, every time the sample mean of all the things are getting different. So if he done 3 sampling, the sample mean is different. That means it's a random variable. Every time it's getting different. So if we'll start, see, I told you that if we'll start increasing the number of samples, right? Earlier it was 5. So we were getting sample mean as very different from the norm, because we should be getting the mean value should be closer to 0, right? So when I was doing the sampling with sample only 5 samples, at that time I was not getting the value closer to 0. When I started doing the sampling with number of samples as 20. Okay, so when I started doing the number of sampling 20, so in the sampling first I get the value 0.08. That is much closer to 0, respected to 0. Like minus 0.25 or 0.17, right? In the second sampling, when I got the value as 0.24. Okay, in the third sampling, yeah. So here the number of n we are not increasing so drastically. That's why we are able to see that the value of the sample mean is also not changing much, because here also whenever I was taking samples value as 5, so it was the value of the sample mean was 0.25 minus 0.25. Here when I starting 20 also, we got the sample value as 0.024. Now I'll start okay. Now I started taking the samples of any sampling as 200. Now it will start converging bit more. See, now it has started converging to 0, right? See. So the sampling first we got 0.1 minus 0.1, 0.01. The second we got 0.11. The third we got 0.12, some sort of thing like that. So whenever you start increasing the number of samples in any sampling, you'll start getting the value, the mean, a bit closer to the population mean. Okay, now he has done for the 1,000, like any sampling, 1,000 number of samples. Now it's getting closer or more, like 0.04, minus 0.04. Okay. So now the expected value and the variance of the sample mean. Okay. So the expected value everybody would be knowing if I have some population distribution. So the expected value of the mean would be what? The population mean only, right? So the expected value of the sample mean would be the population mean itself. So there is nothing like need to prove. Like it's a simple, like if you will think also, if you are having some if you calculate the sample mean, the sample mean was random variable, right? So for all the samples, all the sampling, you were getting the mean as a bit different or maybe a bit closer to each other. But the value, the expected value of all those mean value will be what? Will be population mean, right? This clear? Is this clear?
Yes, sir. It's clear, sir.
Sir, yeah. Can you repeat last line once again?
What okay. You said just. So if you are doing n sampling, we are doing from some population distribution. Okay, this is IID. I'm just talking about IID. So I did that sampling. Okay, and every time for first sampling, I calculate the mean value. That mean value will be x1. Just don't get confused with anything. The first mean I calculated was x1 bar. This is according to the first sampling, I got this as the sample mean for the first sampling. For the second sampling, I'll get some other mean, or maybe a different mean, but small, closer to this one, maybe same as this one. Okay. Again, we are doing n sampling, so we'll get n sample mean. Okay, and all those we mean. So now I'm having n sample mean, and those n sample mean, somebody can ask, right? So what is the expected value of this? The expected value of this mean will be population mean. Or you can think in this way also. If you are having some samples mean, so it will converge to the population mean only, right? So the expected value is what? The expected value of this sample mean would be population mean only, right? Is it clear now?
Sir, I got it.
Yes, sir.
Okay. So in the same way, the variance has been calculated. So the variance of the sample mean is the variance. This is not the sample variance. Okay. So the variance of the sample mean. So this is two different things. One is the sample variance. Sample variance is simply you have one sampling, you did one sampling, you can calculate the sample mean of that sampling, you can calculate the sample variance of that sampling. Okay, that is another thing. But here it is the variance of the sample mean. The variance of sample mean is the population variance upon n. This is what I was telling. If you'll start increasing the number of n, you'll start getting the variance as very small, like because it's a 1 upon x graph. So 1 upon x means we'll start increasing the value of x. The variance will start decreasing. If the variance will start decreasing, that means the mean value will start getting the sample. This is the simple normal distribution. Okay, whenever we'll start decreasing the sample variance or start decreasing the variance, that means the curve will start doing like this. The curve will become like this. This is the mean. So that means variance is what? Variance, by definition, it is the spreadness, how is the data has been spreaded from that mean value. So if you are having lesser variance, that means the spreadness of the data from the mean is less. That means the sample mean is getting closer to the population. Okay. So whenever you start increasing the n, the variance of sample mean will start decreasing. That means the variance is decreasing, means the expected value or the sample mean will start converging toward the population.
Sir?
Yeah.
Here the question comes, like on this side, also, be on this side, sir. As you said just a couple of minutes back, like we have done n sampling, right?
Yeah.
And we got each time a sample means say x1, x2, x3, right?
Yeah.
So when we are saying variance of sample mean, does it mean that variance of all those means we are calculating? Does it mean that? Does it mean that?
Yeah. That is, otherwise if the value is same for every time.
That is so we are proceeding in the same way. Like once again, I will calculate the mean of all the means, right? And then I will again use the formula x minus x bar by n minus 1, right? So
yeah. So if you are see if you are having, you'll be having some mean for n value n sampling, right?
Yes.
For n sampling, you'll be having mean. So all the mean will be different. Like
let us write down few values, sir. Like around 50, we can write it down few values like 50, 48.
Yeah.
50, yes.
Right. So,
yes.
And 50 is the mean sample, like mean of this mean.
Yes.
Okay. So now if we'll calculate the variance, this is what we are saying. This is this thing, the variance of the sample mean. And you can calculate directly by sigma square upon it.
I have a question.
If I don't know anything about population, so from where I will get sigma square, sir?
Yeah. So if you have only the population thing, you can directly, yeah.
Yeah, if I don't have any idea about population, then how I will get sigma square?
Then you'll not get, right?
So at that time, can I
So
use
the parameter of the population should be there. Then only you'll be able to know. Otherwise, you have to calculate with mathematically.
So in that case, can I use variance of my sample mean as the variance of my population?
Variance of the sample mean
as variance of population. Can I say that at that when I don't have any clue about the population?
No, you can't say that. You can't say this thing. If you don't have if you are not knowing about some parameter of the population distribution, you can't directly say regarding this is almost similar to the sample mean or whatever you're calculating. This is not correct.
Sir.
Yeah.
I'm sorry for being so dense.
No,
I
it's fine.
understand the first line, like let x1, x2, xn be the ID samples whose distribution has a finite mean mu and variance sigma square. We are talking about here the expected value of the sample mean, is it?
Yeah.
This first line?
Yeah.
And the variance of the sample mean, this is the variance of the sample mean that we're talking as sigma square. No, but this is the population mean, right?
Which one is population mean? This
Sorry,
one.
The first line. I'm talking about the first sentence.
Okay, yeah. This is population, right? This sigma square is for the population. This is mu for the population.
I am unable to visualize this statement. Let these be IID samples whose distribution has a finite mean mu. Means what? Basically, the random variables belong to a population which has a finite mean mu and a population variance of sigma square. Is that what it means?
Okay. So see, we are having some parent distribution, right? Or the population density. Okay, so I'll just show you. So we have one population distribution, right?
Yes.
So this population distribution will be having some parameter. Will be having some parameter, right? So that parameter is mu and sigma square. So if this is a normal, so normal will be having, if this, for example, this is a normal distribution. So normal distribution will be having some mu and sigma square, right?
Yeah, of course.
Yeah, so this is what has been the sigma. This is for the population distribution. It's given for the population distribution.
Got it.
Yeah.
And x1, x2, xn are basically the samples, my samples that I take. Normally here we have been given the population parameters.
See, it's written capital X, that's why you're getting confused.
Yeah.
Okay. So, okay, then don't see this. You can so it's just like the way of writing. Everywhere it's written like capital. So the sample mean for the first, what you can say, distribution, first sampling would be x1 plus x2, this thing.
Yeah, I think I got you, sir. Thank you so much. I think I got you. Thank you.
I have a question here.
Yeah.
For expected value of x bar square, are we squaring the entire expected value of x bar, or how is that we're getting this?
This one, the second line. The second line, right?
Yeah.
Okay, so that what is the formula generally if to calculate the variance? Is calculated as
E minus x square minus
E of x
whole square.
Whole square. Yeah.
This is how generally calculated. Okay.
Correct.
Okay, fine. Okay, so second line. I'm just missing something.
Actually, we can find that out from the equation above, right? X bar is
how the second line
plus etc. plus x and y n.
Third line, okay, this we are doing this. Second line.
Yes, sir. Please explain how the two key x1, x2 parts come.
Okay. So okay.
So we can
If
use
you have
that
to
equation,
calculate, okay. So if you have to calculate the expectation of something, how generally you calculate summation of this x to this px, right?
Yes.
Okay. If you have to calculate the expectation of x square, we'll calculate x square, and then I guess this is, what is the method used?
We still go with the product of this and probability of that particular value which translates to.
I guess I'm missing something. Does anybody has clarity in this?
So in the box above, it is written that the sample mean x bar is equal to x1 plus x2 plus etc. up to xn by n, right?
Yeah.
And aren't we just, didn't we just take the expectation of the squares from there?
No, we can't do that, right?
Is it we can call this as movement from mean?
Moment.
Is this that thing?
What the other gentleman said, squaring the one x bar is equal to x plus x1 plus x2 to xn by n.
Squaring, I guess.
Both sides, and then applying the expected values. Is that what it is? Seems like.
I mean, the equation is kind of looks like that, but I'm not really sure anymore.
I also have not. Okay. Oh, okay. I'll just open the lecture itself. Maybe. So this is the second lecture, right?
I think so.
I just missed the point, I guess. This is not. Okay, this is the second lecture. Here it is, right?
Yeah.
I guess I'm missing something.
Is it the moment?
Yeah, this is moment only. This is a moment only, but I'm asking how did we write? Like, I'm just missing something, I guess. Yeah. Okay, maybe we can discuss in the end, or maybe if any this this is a basic formula only, but I don't know how. Like I know, but
excuse me, sir.
Yeah.
Here we are squaring the x bar.
We are squaring the x bar.
X bar. Then we get x1 square, x2 square, etc. to xn square.
Okay.
To x1, x2.
No. How can you?
Like that. Then we take the expectation of that. Then we will get expectation of x1 square.
Okay. So this x is what? This x is what? This summation of this opponent, right? Whole square. Right. Okay. I got it. This is what I was using some basic form. So yeah, so you can write this x is in this form. So this x is what? Summation of x1, x2, xn upon n, right? So this you can directly write in this way. Okay, similarly, if you have to calculate this expectation of x square, x bar square. So x bar is what? X1 plus x2 till xn upon n. This is the expectation, right? So if you are calculating that, can come in the form of linear transformation where x1 whole square plus, okay, and then if every other term. But the thing is, if we are writing in this form, okay, all the other things.
X1 is to x2 are identities. Therefore, we can write it as 2 into x1, x2.
Yeah, that this we can write in this form, because every time that some two number will come, and that can come in the product because independent thing, so it can come in x1, x2.
There are n times, n minus 1 times only. Then we can write it as n into n minus 1 into n divided by 2.
Yeah, okay. So okay, this is fine. My only concern is, okay, so only two things will be coming together, or either three things will also come together. That is my only concern. I don't know. I need to check it and then I'll get back to you. But I guess this is the correct method, whatever she's told. So if you are able to write this x bar in this form, then this x1 whole square plus the expectation of all the random variable, whatever you getting the whole square, and then if you are taking two numbers at times, like for example x1, x2, or till x n minus 1 x, and so you'll be, but okay, yeah, that's this fine. So x1, x2, and again if you'll get x2, x1, so just adding those things, so you'll be having 2, and then 2 will become common for all the other terms, and all this are independent to each other. Okay, why my only concern is the if you are having something in the squared form, so whether it will take the 3 terms, I don't know. I need to clear this. I need to check up on this. Okay, then
The expansion of a plus b plus c the whole square is a square plus b square plus c square plus 2ab plus 2b. Then
yeah, so you'll be having
like that.
Okay, so you'll be having only 2 terms each time, right? You won't get a b c in the a plus b ka plus c ka whole square, right? So you'll not get any c terms. So then that is fine, right? Okay. So who was asking, is it clear? See, I'll try to explain it again.
Yes, please.
Okay. So this x can be written in this form, right?
Yeah.
Okay. So if it's written in this form, I don't know if this okay, so this we are doing the squared thing. This expectation we have to calculate the squared of this one, right? So the squared of this one, so 1 upon n square is you are taking outside, and then if you are doing this square, and then you are putting the expectation on this bigger polynomial. This is in the form of some quadratic, not quadratic, this is some linear combination of x1 k square plus x2 k square, that you can use the expectation directly on those, right?
Okay.
Is it fine? You can use the expectation directly on those. And now if you are, so she told one like this pretty simple, like if you are having a plus b plus c ka whole square, you'll not get any term will be having more than 2 terms, right? So you'll get the terms, the combination of a b b c, or
and c. Yeah.
So here also you'll get all the term in the combination of x1, x2, or in the similar way you'll get all the combination. Like if you are having n, so nc2 you'll get, right? So you'll get the combination of 2. So if wherever you are getting the combination, you can write in this way: expectation of x1, x2, right? And that can be written in this way: expectation of x1 multiplied with expectation of x2, because both are independent of each other, right?
Yeah.
Okay. Okay, so now what has been done? So this term will be having n terms, right? Because from n to
yeah,
so now
that is NE. Okay, right, got it.
Okay, for this term, what is this? This I'm having. So this I was having how many terms? Okay, so here we got okay, so we got this n from here, and then this all x1 chi square, x2 chi square is terming to the mu square, and then I'll be having this. If I'm getting n here, okay, how will I get? There is is fine. And how we are getting from here n into n minus 1 from mu square. So x1 ex1 and ex2 generally gives us mu square. So we'll be having this mu square and okay. So I'm having okay. So if I'm having n terms and I'm taking out 2 terms each term, so this would be NC2. And how can we write NC2 in n into n plus, so n into n minus 1 upon 2, right? But okay, got it. See for example this one, if I'm having a plus b plus c ka whole square, so what you'll get, you are having 3 numbers. So out of 3 numbers you'll be getting combination of 2, right? And in combination of 2 you'll be getting ab and I guess b, so you'll be getting
AB,
2
BC,
times
CA.
AB, right? So you'll be getting AB and again BC, CA, and I guess twice you'll be getting each.
Correct.
Right?
Yeah.
So 3C2 is what? 3C2 is 3.
Yeah.
3C2 is 3. So you are getting 6 numbers. Like you are getting 3C2 multiplied with 2. You are getting simply the permutation of this n. So you are getting 3 into 3 minus 2 term. Are you getting my point? Like we were having 3 terms and we got this combination of 2 terms as six terms, I guess, right?
Yeah.
So here, I guess in the similar way, if you are having n, so you have to you need to confirm that if you are having n terms and out of that n terms, you are choosing 2 terms each time, right? Like for example, I choose 1, 2, and then 1, 3, 1, 4, 1, 5. So NC2 you are choosing, and each term is coming twice. So you are multiplying with 2. So you are getting n into n minus 1 term. So I guess this n into n minus 1 you are getting from there. Am I right?
I'm just wondering, you wrote it as 3 into 3 minus 2, but here it is n into n minus 1.
Which one?
The expression is n into n minus 1 mu square.
Yeah.
So you written it as 3 into 3 minus 2 over there.
Yeah, this n, because I was having here a, b, c, and n here is 3. So again 3 minus 2, that is the n minus, not 3 minus 2, 3 minus 1. N into n minus 1. So here it was 3, n was 3. So 3 into 3 minus 1. Did you get the point? Like, see, I'll just square this term, a plus b plus c.
It's going to be a square plus b square plus c square plus 2 times ab plus 2 times bc plus 2 times ca. That
so
part is clear.
Okay, so 2ab you are getting plus 2bc you are getting plus 2ca you are getting, right?
Correct.
So you are getting 6 term. Fine?
Yes.
Okay. So you got 6 term means 3 into 3 minus 1 or n into n minus 1.
Oh yeah, okay.
Fine. So here, if you are having n terms, you are getting n into n minus 1 term. This is n into n minus 1 term. Why mu is square? Because expectation of x1 is mu and expectation of x2 is also mu. So mu into mu is mu square.
Okay.
Right?
Yeah.
So now it has been expanded in this form.
Okay. N into e x square. Why is it written as n sigma square minus n mu square?
So this is what?
The first part. Now let's go to the first part. Yeah, n e x
one.
square. Yeah, that one. It is written as when it comes to the next expansion, it is written as n sigma square plus n mu square.
So this is n mu square
plus n sigma
minus
square.
n sigma square, right? Okay. So
No. Sorry. It is written as n sigma square plus n mu square.
Okay, 1 second.
Okay, it's basically the equation for variance. Okay, fine.
Yeah,
fine.
so that has been subtracted from the.
Okay, got it.
Yeah.
Okay, thanks.
The proof and all is okay. So I also didn't see the proof, so we did it here itself. So it took our, I guess, more than half an hour, but it's fine.
Thank you.
Yeah. So I guess somebody is asking Hari Shankar. Like, it's a confusing session. I agree with you, but the terms and all is very confusing. But in the, I guess, calculation part, you will not feel any confusion, I guess. So till now it's fine. Like Hari Shankar, Meena.
Okay. So can I say something?
Yeah.
When we are expanding the x bar, the whole x bar square, we will get x1 square plus x2 square up to xn square. Then we multiply the entire thing with 2, like x1 into x2 plus x2 into x3 plus not exactly x1 into x2 plus x1 into x3 plus up to x1 into xn. Then we start from x2, like x2 into x3 plus up to x2 into xn. Then we multiply with x3 and up until then by during each when we start multiplying with each term, the number of terms are decreasing -1. So what exactly is happening is we are getting sum of the mu square will be 1 mu square plus 2 mu square up to n mu square. So it will be n into n minus 1 by 2 mu square, and we have a 2 outside, so that 2 will get cancelled. So that I think that's how we will get n into n minus 1 mu square.
So either this way, or you can see the example of A. So there also it was the same thing, AB plus BC plus CA. And we were having this 2 here. So we just do it like 3C2, right? This is what we did, right?
Yeah.
Okay. So this is the sample mean and the sample variance of the mean, like the variance of the sample mean. Okay. So if you have been given the population variance, you can know regarding the variance of the sample mean. Okay. This is the one thing that you can calculate. So many of the questions, I guess, in the grade or practice is similar to, like, you have been given the variance of the population, you have to calculate the variance of the sample mean. Sample mean can be calculated simply. If you are having the samples, you can calculate the sample mean. For the variance of the sample mean, you need to know regarding the population variance, and then you can calculate this. Okay. So I'll just go through the whatever the slides now is left. So this is what I was telling you. The variance of the sample mean is tending to 0. Like, we are increasing the value of n. So if you increase the value of n, so all the values, the x bar will start converging toward the mu. Mu is the population mean, right? And this is the sample variance that we were talking. So sample variance is, you'll calculate if you are having one sampling you did, whatever the samples you are having, you have to calculate the sample mean, and from that sample mean, you have to calculate the spreadness, and then you can divide with n minus 1. Here, you have to divide with n minus 1 to get the sample variance. So the upper part was different thing. This is the different thing. This is the sample variance simply. The upper part was the variance of the sample mean. Okay.
So sample variance means variance of sampling one or variance of all the sampling.
Sampling one only. So one sampling you did, you got some samples. So for that case only, if you are doing for all the cases, that you don't think it will start converging to the population variance.
So that will be known as a variance of the sample mean, right? And
So
this
the
is the
sample mean.
And this is sample variance. Sample variance means, 1 second, with respect to example, I did sampling 1 and I picked 10 objects, right? So this is the variance of these 10 objects, right?
Yeah. So see here, given a sampling x12, so this here it is written as small n. So this is the, you can refer this. The value taken for the sample variance s square is s square. So here s square and s square are both same. So don't get confused with s square. Why it is written capital X1? So it's then simply the small x1. So you have the samples as x small x1 to x small xn. This is the sample value corresponding to some sampling. Okay, and then you can calculate the sample weight. Is it fine? Is it clear now?
Yeah, so can I ask a question? Suppose we are given, like we have done 10 samplings, and for each of those samplings, we have got like the sample variances, right?
Yeah.
Now, if we are given this and we are asked to find what is the sample, what is the variance of the population, can we do that? Can we calculate that?
No, you can't calculate.
And what would stop us from getting there?
Because you are having only 10 samples, like you did 110 times sampling. You are not aware of how many what are the population sample, like what are the number of the samples in the population, right? You're not aware of that. You can just predict. You can't exactly, you can't tell. This is what I'm saying.
Now, if the whole population itself is 10 times into the number of samples in each testing,
then also it's not correct, because you can get the samples from the repeated time. Like, see, this is the population. Maybe from whatever algorithm we are using, you are using the algorithm such that is giving you the random samples from only this boundary, this from A to B. Okay, you are doing the sampling 1,000 number of times. Every time the algorithm is giving you the same samples from this duration, right?
Okay.
That can be one possibility, right?
Yeah. So if the samples actually in each of these experiments are
sample okay, with some maybe in the next week you'll read with some estimation, mathematical estimation, like the Bayesian estimation or maybe the maximum likelihood estimation, you can just estimate the value. Estimation doesn't mean you're just that the value is pakka, right? Like the confirmed value.
Okay.
So estimation, you can do some mathematical interpretation and can estimate the value of the population mean or population weight, but you can't exactly say. This is what I'm saying. Okay. From the samples, like if you are having only like there are some method also like central limit theorem and all, where you are doing the samples, you are collecting the samples from the same population again and again, like did for 1,000 sampling you did. So in 1,000 sampling, what you'll start getting, you'll start converging to the population itself. Like if you'll start increasing the number of samples also, what happens? See, even if this is the population, right? Even the samples, whatever you're collecting, okay? Like for example, you did collect one sampling. In first sampling, you collected 10 samples. Okay, so that if that is a totally random sample, the algorithm is not biased and anything. So that algorithm will give you some numbers, like for example, it will give you 10 numbers, like for example, from here. So some 10 values, and that 10 sample will also be a similar to your probability, like that is your population distribution, similar to, not exactly your even the first sampling. Again, if you will start doing the sampling for 10,000 times, so you'll get almost all, not all, but you'll get most of the samples from that is same to that of the population, Okay, so it'll start resembling the same normal distribution, same population distribution from that sampling itself, right? Not the exact same, but you'll get a similar sort of population distribution where the the value will start converging to your final value. Fine.
Okay. Okay.
So knowing the sample variances won't help me get to know the population variance. But knowing the sample means, and if we increase n, then we can get to know the population mean. Is that what you're saying?
We'll approach population mean. We may not actually get the actual mean itself. At least that is my understanding.
Can you repeat that?
No, what I'm trying to say is that, like, if we calculate the sample means, we can arrive at the population mean. But knowing the sample variances, we can't get to the
No, from the sample mean also you're not. How did you get the population mean? Exact value, how did you get the sample? From
like converging. Increase n, if we keep on increasing n, you get that it would.
Then you'll start. Yeah, your value will start converging. That doesn't mean you'll get the exact. The value will start converging to the population.
Oh yeah, there's this fine print there, right? I forgot.
Right. Is that applicable for variance also? Like for mean, it starts getting converged, right? Is that applicable for variance also with the help of sample variance?
Okay, so for the sample variance, see, that was a different thing that I guess you are clear at least regarding the variance of the sample mean. So variance of the sample mean was a different concept. Okay, so the samples, if you are starting collecting the sample variance, okay, so sample variance you calculated for some first sampling. Okay, then you started doing for many sampling and all. The expected value, I guess, generally get converted. I'm not sure about this, that I need to see. But the expected value of this S square will also start converging to the sigma square. I guess this is correct, right? I guess most of you are.
Can you repeat that once again, please?
Okay. So the expected value of this is, see, this start converging to the sigma square.
Expected value of the variance.
Sample variance. It will start.
Expected value of the sample variances will converge towards the population variance, right?
It will start increasing the n. And
yes, it will start increasing n. Yeah, got that.
Yes, sir, we got that.
I guess this okay.
But isn't that the one you established a little earlier in the previous slide?
So that was a different
sigma
thing.
square by n.
Okay, so that was C. That is what I'm saying. This C. So you have done one sampling. So for this sampling, you can calculate mean or sample mean or sample variance. So if you are calculating for some samples, that simply mean that you're calculating sample mean or sample variance. Okay, right. This is one thing. Second thing is sigma square by n. Sigma square by n is a different thing. Sigma square by n is the variance of sample mean. Variance of sample mean. And this is the sample variance. These are two different things. Sample variance means I'm taking the samples in first sampling and calculating the procedure I'm telling you. The procedure
okay, so variance of the mean is what you are saying is sigma square by n.
Yeah.
It's not the variance of the population. Okay, variance of the mean. Okay.
Yes. If you start increasing the n, that means what? The variance will start decreasing. Variance start decreasing means the spreadness of the data from mean value will start decreasing. That means this sample mean will start converging toward the population. Is it clear now?
Clear. Thank you.
Okay. Thank you. So this is the sample variance formula. This x1, x2, don't get confused with the capital X1 and capital X2. So if you are having some sample, n sample, that in the form of smaller x, so you'll be having some numerical value. From there, you can calculate the variance. Okay. sometimes it's n minus 1, sometimes it's n. So here you have to use n minus 1. Okay. Yeah, so this is what I was saying. So X1, the IID sample whose distribution has finite variance sigma square. So the sample variance is as expected value given by this. Okay, so the expected value will be the population variance. This is the expected value. Because so in the expected mean value was also what? Expected mean one also the population mean. Expected value that expected sample mean or the expected sample variance is what? There it was population mean, there it is population variance. Okay, this is the expected value. So don't get confused with anything else. This is just expectation.
Oh, this expected value of sample variance, right? So like
Yeah.
I did sampling 1, right?
Hmm.
So I got 1 sample variance. I did sampling 2, I got 1 sample variance, right? I did sampling 3, I got 1 sample variance. So this is the expectation of all those 3 sampling, and that will converge to sigma square.
Yeah.
Does it mean that?
Yeah, yeah.
So as a layman, expected value means long-term average, right? As a layman, expected
Yeah, you can
value
say
means
that.
long-term average, right?
Yeah, you can say that's a long-term average.
So if I calculate average of those variance which I'm calculating for each samples, will it converge to population variance? Does it mean?
So if you are calculating the sample variance for a number of
sampling, I did sampling 1, I did sampling 2, I did sampling 3, I did sampling 4, right?
Yeah.
So I calculated variance
The
of each
expected
sampling.
value, yeah. So the expected value of those S square will be sigma square. Yeah, correct.
So expected value means I will take average of those 4 variances.
Yeah, correct. The expected value is what? The average value of all the sample variance, whatever you calculated from n number of sampling. Is it fine?
That's my question. If it's a valid statement, then of course I will stick to that.
So this is what I'm saying. This is how did you how generally you calculate the expectation of anything? You generally calculate the average value, right? So if you are doing the sampling n number of times, you got some sample variance, right? N sample variance. If you are calculating the average, you'll get the not that it will start converging toward the. If you have to calculate the expectation, it will start converging toward the population variance. So it's written here also. So expected value of sample variance equals to the variance of the distribution. So the expected value of the sample variance. So the expected value of sample variance means what? You're just calculating the average of all the sample variance you have calculated, right? Is it clear?
Yes, sir.
And the values of the sample variance on average will give the when the value if n increases, the sample value will be closer to the. See, this is written. If we will start increasing the n, sample variance takes value closer to the distribution variance, right? So we will start increasing value of n, it will start giving you the sample variance will start getting closer to the distribution variance. Okay. See, so I was having seen this Bernoulli, okay, with mean this and variance this. So sample variance I've calculated for n equals to 20, right? So for n equals to 20, what I was getting the variance as this one. I started increasing the number of n, we have increased to 200. Okay, so 200, that means this means what? This means the sample variance of first sampling. This means the sample variance second sampling. So similarly, we did it for the n equals to 200, right? This is what has been written. And if you'll start increasing the value of n, you'll start getting the sample value, sample variance closer to this population variance, right? Is it clear?
Yes, clear. So like say, let us say third example where n is 1000, right? So where n is 1000, I did sampling 5 times and I got 5 sample variances. And if I take average of this last 5 numbers, so it will come very close to 0.25. That's what we are agreeing, right?
Yeah.
Okay.
Sir, I have one question here.
Yeah.
Like when normally we do sampling when because we cannot take the population completely to infer some populations. So as you said that the more we take the sample and it will represent the population variances. So would you recommend like the sampling how to calculate the number of samples? Like for example, should I take 5, 10, 15 out of my population data set is 100? So is there any base that should I take this many samples to get the
as you
appropriate?
start increasing the number of samples, you'll start getting the good values. So this happens every time, like in ML also, whenever you give the algorithm the number of more data points, you'll get a good accuracy, right?
That's true, sir. But let us say I do have a data, and let us say I do have to solve a business problem. And the data the company expects me I need to derive some decisions for that particular problem.
Okay.
So they have a millions of records. Let us say sales record of a particular product. Now, how do I arrive? The sample.
The
How
number
many
of
samples should I
samples.
take? Should I take all the 1 lakh population?
No,
Like how
then
do I get the number of samples? Yes.
okay. So what here? See in the Python, what you can do you can plot. Okay, so no, there is that also will not help you to plot. So similarly, like normally what happens in ML and all, generally we start. So if you want to know the number of some exact thing, but just plot the accuracy versus that number of thing. And if you are getting, okay, that is a different thing. But here, what if you want to know the exact number of samples, that exact number of sample, I don't think so. I'm not, maybe I'm wrong, but I don't think so. There is any method by which you can predict the number of samples that will be the correct resemblance to your population distribution. There can't be any exact method to know regarding the samples number, but only one thing we can say, you can start because if you are aware of the population, everything about the population thing, why you will do why you will work on the samples, right? So you must be not be aware of the population parameter. That's why you are working on the sample data set, right? So
yes, sir. That's the reason. Like I need to derive decisions from the sample only. Now, should I let us say my friend will take 10 samples and I am going for 15 samples, and my another friend will go for 25 samples. Then obviously the result will be different, and I cannot arrive at a particular decision which I need to give to the management. So in such cases, like I should have a base. Like okay, I need to this is the at least approximate way to calculate the
G-test
number
and
of
all,
samples.
what you did in G-test or T-test and all, like that hypothesis testing, generally we start with at least it should be 30 data point, like the samples. But I don't know in this method what would be the same. Like in all those tests are pretty different from this thing. But in those cases, generally we start taking at least that maybe you would have heard about if you are working or if you are went through that G test or A/B test and all. There we used to start, if I'm not having 30 data points, I'll not work. Even to work, I need some 30 data points or something like that. Here I'm not, I can't say what would be the exact optimum number of that samples that will help you. But only one thing we can guarantee, as we start, like you took 100 and then you took 1000, then the accuracy for your parameter will start increasing. This is what I can guarantee only. Other than that, I don't know what is the method to get the optimum samples number, and that depends on the problem to problem, I guess. Like for example, if you are doing some that in that many a times you would have heard. So see what happens in the that election polling, like not that polling, what they did before that result, something that, what is that, exit poll, or what generally we call that.
Yes, sir. Exit poll.
Exit poll, right? So their exit poll is that thing that they generally take the smaller sample from those constituency, right? And based on that, they'll predict something, right? There is a small samples out of that population samples. Population samples will be like the number of people who gave the vote, right? in their constituency. So in each of the constituency, they generally take some samples from those people, whoever has voted. And from those samples, they start predicting. Many a times it is wrong because that is not resembling to the population thing, because the number of samples generally they take is very small. Because if the in our country, like in the Lok Sabha election, if all over the India, if it's happening, so you can presume that at least what 1/5 or not 1/5, but at least 1/10 of the people would be voting, right? So out of that, the samples generally they take is in number like 10 lakhs only. So those samples is pretty small as compared to that 10 crores or whatever the number of people who generally vote, right? So that's why we can see that many a times the exit poll generally doesn't resembles the population things, right?
Yes,
If they were aware of the number of samples, what would be the optimum number of samples, if they were aware of that, they would have used those methods to know the optimum number of samples so that I can resemble the population thing. And every time the exit poll will be almost similar to the final result, right? So there can be this, I don't think so that there will be some method to get the optimum number of samples that will predict, that will be almost same as the population. Yeah. So, okay. So this is, I guess, so this topic is not consist of much concept, but it's too confusing because of the term or the samples, that the term or the thing that with which we are representing the, that's why it's become a bit confusing. But
that's a challenge.
Yeah, but I guess if we'll watch the lecture twice, I guess there won't be much issue, right? If you'll just watch, because there is only 4 lecture. Out of that 4 lecture, you can exclude the first one. You can start watching from the second lecture itself. Just watch the second lecture twice and watch the 4th lecture twice. So maybe
to cover more, sir. They had to cover more inequalities are there, sir. Can we proceed?
Yeah. Okay. So I'll just go through. Yeah.
Yeah. I was just going to ask you what is the difference between sample and sample proportion, but yeah.
Okay. Sample proportion. Sample proportion is simply some part of that. Like here it has been represented, A is represented at X greater than T. So that if you have to calculate something regarding that A, that means that you have to calculate everything where X is greater than T. Or A has been defined as X is between A and B. That is the part. Like for example, I have to calculate the probability of A. Okay, that generally represents the sample proportion, and where X is between A and B.
So is the number of samples between A and B?
Yeah, so if we are doing IID and that represents only the success and failure. So between that A and B, what are the number of success upon the number of all the terms?
So can you take some verbal examples? Can you please explain?
Okay, so there will be, I guess, so here the sample proportion of A is what? Xi for which A is true upon all the number of samples in that interval. Like for example, I took, so between A and B, there were 10 points. Out of the 10 points, 5 was success and 5 was failure. So 5 upon 10 is the sample proportion for A.
So did you get probability, no?
Here it will, yeah, it's a probability thing only. So the number of success for which A is true upon the total number of. So maybe there will be more examples, I guess. Okay, so here I was having some, 5 samples, out of that 3 was success, so 3 upon 5. So n is the number of that total number of samples. Out of that, how many are the positive, or how many of those are true for us, or how many of those that we have defined already is success for us. So like for example here, the sample proportion we have to see is X less than equals to 0. So X less than, out of that 5 samples, whatever we took, how many of those are like less than 0 here? So we have defined that sample proportion as X less than 0. So out of that, how many are less than 0? So 1 and 2 is less than 0 out of 5. So 2 out of 5. Okay.
Sir,
Yeah.
may I say something? It just looks like instead of P, capital P, we are just replacing with S. So we are doing nothing but the probability, right? Why do we need a sample proportion when we are just calculating the probability?
So it's like, how will you say, okay, so for this sample, the so this is almost similar to this, not exact probability. We are just calculating the sample proportion out of the samples we took. Okay, so what are the sample we took out of those samples? How many of them are representing whatever we need? This is what the sample proportion tells you. Probability.
But what we saw from this empirical thing on the second lecture, it says that the number of times where x is true divided by it gives us a probability, right? And it's coming here again. How is that different? I'm unable to get.
It's nothing different. Only here some sample proportion. This is the new term you have been going through.
So there must be some.
Yeah, I'm sorry. I'm probably a bit trying to.
No. It's fine. Like, it's totally fine. Whatever you're asking is totally fine. I'm just telling you the sample proportion here. Generally, see the examples here. You can see how it has been defined here. Let A be an event defined using X. Okay, and what are the X? What are the X there is defined as my proportion. Like, for example, I've been defined A as in proportion, where X is greater than T. X greater than T or X greater than equals to 0, or whatever the sample you took, like you took 500 sample, out of that 500 sample, how many times this is greater than 5, or whatever the proportion you are taking out. Okay, this is just a simple way to calculate. Even you have been not taught this sample proportion, you have been asked, you would have told the same thing, right? Even if you have not been taught this sample proportion, if you've not been taught this word proportion, if you have been asked to calculate the proportion such that x greater than 5, you'd have told the same thing, whatever it's written here, right? Without even knowing the sample proportion. It's a simple, this is just a simple, what do you can say? Word.
Sir,
okay.
Sir,
Yeah.
Let me put my perspective why I'm asking this question. You rightly said that we could have told, I could have told the same thing without even going through this slide.
Yeah.
When we start studying probability, the first definition of probability was told to us that number of interested events divided by total number of events, right? This was the first definition told to us. Number of interested event in the numerator divided by total number of events. And the same definition of proportion is given here. So my question is that why a new terminology has been introduced? There must be some significance of bringing a new term here. That's my question.
Okay. See,
because this proportion is as good as probability. The definition which I learned, in my very first day of this course, that number of interested event by total number of events. So say for example, I am tossing a coin, right? 10 times, I got 6.
Okay, fine. Okay, I got you.
So why a new term has been introduced as sample proportion?
Okay,
There must
so can you define one thing I'm asking you? Can you define this S probability? Okay, for this cases you can.
It is 3 by 5.
Can you define? Okay, can you define this as a probability X less than equals to 0?
I will find out all the values.
You can't define this as a probability
Just a
of X.
second. I will find out all the values where my X is less than 0, and I will find the ratio of that. Like there are 2 instances where it is less than 0, so 2 by 5.
See, why you are saying this?
So 2 is my interested events and 5 is my total number of events. So that fits my definition of probability also. So what is the difference between proportion and probability?
Not fitting. See, okay, fine. See, you can tell here like the probability of X less than equals to 0 is equals to 2 upon 5. So, but how generally you calculate the probability? If you have to calculate the probability of any distribution between X equals to 0 to 1, how generally you calculate the probability? You can't calculate just by counting the numbers. What is the between X0 to 1 and then divide it? Like if you have to been asked regarding from some distribution, you have been asked to calculate the probability between 0 to 1. How generally you calculate? You do the integration, right? So you can't define the same thing here. Like you can't say the same thing. Maybe the method here is the same because you are getting the district.
Sir, I know I am wrong. I'm just trying to find out the answer. As you said, no, you are saying that integration, right? Integration is done for continuous random variable. For discrete random variable, we simply count and divide.
Sir, excuse me. Would you allow me to answer this question like here?
You can.
So here proportion means, Gagan Prasad, here proportion means like you are calculating, no, how much percentage you score. Let us say I have full marks 100 and I scored 90%. So 90 by 100. Similarly, let us say here question is here, what is the sample proportion? From the population, we take some percentage, like some percentage of that population we take sample, and from the sample, what is the proportion? What is the proportion of that sample? Is the from 100 population and you take 70, or 100 population it is take you take 20? That is only the proportion out of total number. Yeah.
There is no confusion in understanding how proportion is being calculated or what does it mean. The question is that somewhere or in many places, the way we calculate proportion resembles to the way we calculate probability. So it is just a coincidence. It is just a coincidence. It is just a coincidence, or there is some relation. That's the question.
No.
Can I hazard a guess here?
That's what I'm trying to say. It's not the probability here. It's not the probability here. That's what I am just trying to say.
Can I hazard a guess here, gentlemen? Yes. See, if you take a sample from a population, as sir was earlier repeating, you don't know how many of these elements are going to repeat when you pick something from a lot, okay? And how many of these will have the defects is also out of control. You do not really know if it is a probability. Yeah, when you say probability, definition of probability is, but is the probability for the population? We don't know, because all the defects could be in our hand once. When you go and take a set of, let's say, ball bearings from a big box, all the defects could be in our hand. But the rest of the population is not representative of this, no? Probably that's the reason why they are calling it sample proportion rather.
Because they're even like tossing a coin, we know head and tail, but here we do not know, like population is 100, whether like somebody takes 70 or 70, 60, 80, like anybody can take any sample, no number of samples. So now let us say Ramakant has taken 20 sample, or Ravi can take 50 samples. So it like what is the proportion for Ravi? 50 by 100, and Ramakant it may be 20 by 100. So it's like that, very simple. Like it's not the probability means we know the like what is the sample. What you can say sample space.
Probability we are calculating from sample space. Here it is not representing the sample space. It is just some samples.
Total number of n is total number, and out of that, how much we are taking for our consideration.
But these 10 are from sample space only. These are not, beyond the sample space. These are part of, so we can say that these are events.
No, this is population and sample space will be different, no? Because sample space, you know, what is the finite number of sample space. For example, if you're like throwing a dice, so you know, like if there is a 36, like come 6 can come 5.
Any sample is a subset of population only. That's what he's trying to say from very beginning of the class, that we don't know anything about the population, but whatever samples we are gathering, those are part of population only.
Yeah, but you know the sample space.
I got it. Thank you. I got it. This peer discussion was helpful. That what we are trying to say, as Ravi also pointed out, that this is proportion for a particular sample, and it might be a coincidence, but definition of probability is matching with this definition. Thank you, Ravi. Thank you, Ramakant.
Thank you. But good question. Good question.
Yes. Sir, we can proceed, sir. Are you there, sir?
Yeah, I'm there.
Yes, sir. We can proceed.
It was really awesome. Today's session. Okay, so
you said at the beginning that there is nothing much in this session and so much discussion.
I was expecting, but the thing is, most of you have not seen the lecture also, right? So maybe that can be.
No, sir. That is a wrong assumption, sir. That is a wrong assumption, because every Friday we ask this question, that how many of you have seen this app. That is the reason why we request to discuss the concept on every Friday, sir. Sorry, sir. With due respect, I'm saying.
So what happened earlier? We were not having this type of session. Earlier, we used to discuss the problem.
No. Last Friday, Srikanth sir had come. He had come very well prepared, and he took all of us through the entire concept.
Okay, so no. I'm not saying earlier means before this term. So
okay.
before this term we were not having the
No,
concept.
no, no. We were having like in maths 2 every first session. Subhajit
No,
sir,
no, that's not
Subhashis-
that is not what he meant. That is not what he meant. What
No, no,
he's saying,
that
if this
he's
is the
saying
first batch where he's encountering these kinds of discussions. Earlier batches probably this didn't happen because they were smarter than us. Let's leave it
yes,
at that.
correct. That's a valid answer. That's a valid answer. Thanks, Ravi.
Perhaps they were smarter.
So he might be reflecting from stats 2. I am saying that I am giving the reference of maths 2.
Okay.
When we did maths 2 last time, Subhajit sir, Subhashis sir, or ma'am, they used to take us through the, and what I heard from other group that still they are doing the same thing. They are taking first session they are taking to the entire concept, and that's the beauty of having live session, sir, because most of the recorded lectures it's a one-way communication. If I have a doubt about any term, here I will ask.
Okay, let's start.
Yes, sir.
Mostly I take the session ML, like stats, as in, like I take like 1 week, one session each week. Mostly I take. Like for the last 2-3 weeks I didn't take the session. So maybe after 2-3 weeks I do. In ML generally we don't do this. We generally go through the lecture, and then you have you can ask the doubts. So we are not going through the slides, all the slides mostly in the ML. So this is what I was referring to. I was not referring that somebody is good or somebody is bad. I didn't mean that.
No, just kidding. Don't worry.
Yeah. Fine. Okay, so this is fine, and then so this part is what? So the expected value and the variance of the sample proportion. Okay, so this you can, so sir in the lecture generally took one example of the Bernoulli, right? So in the Bernoulli generally how will you calculate the variance or the expectation? So the expectation of the sample proportion of some A generally converges to like this is what you were saying, right? This generally converges to the probability, right? And if you are calculating the variance, like the variance of what is this? Variance of the sample proportion. So in the Bernoulli, how generally you calculate that? You calculate if you are having the probability of something happening is probability P, then what generally the population or the variance of that is what? The P into, I guess, 1 minus P, right? So this is what has been written. And if you have the same thing is written here, what we were doing earlier. So we were doing this, we were dividing that sigma square by n, right? In the starting when we were calculating the variance of the sample mean. So what we were doing there, so we were taking the population variance was sigma square, and then we were dividing with n. So this is what we were doing here also. So if you'll just the same thing, if you'll assume the same, just put the example of that Bernoulli in the backend, and then if you'll see the expectation of the sample proportion is referring like getting equals to the population of that whatever the interval or whatever the A event you have defined. And similarly, if you're having the Bernoulli thing again, the variance of that sample proportion, again, it will be P into 1 minus P upon N. This is what we have discussed earlier also. This is the same thing, only if you'll start resembling with the Bernoulli thing, you'll get this formula or the equation, whatever we are getting. This experience. So he's asking something. So probability the theoretical. So Nachiket has written something. Probability is a theoretical prediction of an event happening, while the proportion is the actual share. Okay, where it is. So can you see that what he has written?
Sir.
In the chat window, Nachiket has written something.
What is variance of sample proportion?
What?
Variance of sample proportion. This slide only.
This okay. So variance of the sample proportion. So just think of that example, Bernoulli example that has been discussed in the lecture, right? So how generally you calculate the variance? We calculate the variance as P NP. So N is simply the 1 minus P. So okay, I'll not put N because again that N will start like N will generally resemble the number of samples, but here the P into 1 minus P. P is the probability of happening into 1 minus P. Okay. And why N? N, you already know we were doing in earlier cases when we were calculating the variance of the sampling, where we we were dividing that sigma square up by n, right? Is it fine or not?
Pardon, sir?
Can you repeat the point?
Yes, yes.
Okay.
It's
so
a problem.
Yeah, go ahead. Maybe I'll try to.
No, I think the part where you mentioned the variance is like for Bernoulli p into 1 minus p by n, that part is clear.
Yeah, so if you will calculate the mean, just convert this total example into some Bernoulli with p as p of this a is some event where a is representing, a is some indicator, you can say, where yi equals to 1 when a is success, and right, and y equals to 0 for otherwise, right? So this is a basic, this has been converted into Bernoulli. Okay, so for those Bernoulli, what would the variance? So variance would be this one, right? PA into 1 minus PA. This would be the variance, right? If you are having Bernoulli, and this would be the mean.
Even Bernoulli or binomial?
Bernoulli, okay, binomial one.
Sorry, I am a little confused now.
Okay.
I'll have to
See, okay. So Bernoulli is what? If you are doing 1 times, that is binomial, and if you are repeating the same thing, that will become Bernoulli. Or maybe I'm using the
Bernoulli is once, binomial is multiple times.
Okay, yeah. So Bernoulli, if you are doing 1 time, that means what? If you are doing 1 time, so what is the like the variance in those cases? Like in the, I guess for 1 case it will be NP, and for 1 case it will be NPQ, I guess, or what is that?
NPQ.
PQ, right?
Yeah, PQ. Q being 1 minus P.
NPQ is variance, I think.
PQ is.
NPQ is variance. NPQ is variance.
NPQ is variance, right? Or for the Bernoulli, what would be the variance for the Bernoulli equation?
Bernoulli, it's only one event, right? So will there be variance in that? I'm sorry. I'm asking all the questions here.
Wait, one thing. I'll just check it again. Where is that?
Variance of Bernoulli is P into 1 minus P.
P into 1 minus P, right?
Yes.
So this is what has been written here. Okay. So where is that? Okay. So this is P into 1 minus P. P into 1 minus P, and this n that you already seen, that n, that when we were calculating the variance of the sample mean, we were getting n, sigma square upon n, right? The variance upon n we were getting here.
Sigma square by n.
Right, we were getting in the starting somewhere sigma square upon n. We were getting, right?
Sigma square by n, but that was the variance of the expectation.
Variance of the sample mean.
Yeah, variance of the sample mean, correct.
Yeah.
This is also variance of sample proportion, is it? Okay.
The variance of SA is the sample proportion value.
Okay, okay.
Right.
Yeah, yeah.
Same thing we are doing, only the name and everything has got changed.
Okay.
Okay. So now what? Okay, so this is if there is any examples in this cases. So this is the same thing. If you are increasing the n, so the sample will become the population or the probability will get the sample proportion will start converging to the probability, and if the variance, and if you increase the n, the variance will decrease. That means the data set is, the spreadness in the mean value is not much. That means the curve will start getting like a mountain, or you can say just like that I told you in the starting, that if you are having some distribution, if the population is getting closer, like if the population is getting closer to 0, that means the mean, all the values or all the whatever the values you are calculating is coming to the mean value, or the here mean means the probability, right? For this cases, if you are doing the Bernoulli or binomial Bernoulli IID, like n number or whatever the sampling you are doing there. So whatever we have read earlier for the normal, like any distribution, simple thing is here. Like we are just assuming in backend we are doing the same thing with the Bernoulli. Okay, so the expectation of the sample, the expectation of the sample, the sample proportion of A we did, and that the expectation of the expectation of sample proportion of A is what? The probability of A, right? And here the variance of the sample proportion of A is what? The probability of A into 1 minus probability of A divided by N. From N, where N we are getting, we already discussed. Okay. So this is the basic example. If we are increasing the N, that means the mean of the sample proportion of A equals to the probability of A, and the variance of the sample proportion of A start converging towards 0, because it's a graph upon X. So if we'll start increasing X, it will start declining. Okay, this is the same example we're doing. We are having some sample, normal sample. We are doing some 5 sampling, where the number of sample in each sampling is 20. If we'll start increasing the number of samples in each sampling, the proportion or whatever we went, the probability of X less than equals to X less than equals to -1 was what? This is the exact value that we have calculated by integrating the population distribution, right? We can integrate it. That normal distribution, we already know the formula, so we can integrate it from -infinity to -1. We got this 0.159, and now with the sample proportion we are calculating. Okay, so with the sample proportion also, if we'll start increasing the number of samples, so this is what we'll get. We are getting whenever we'll start increasing the number of samples in each sampling, so we can see that we'll start converges to 0.159. This is what the same thing we are doing repeatedly with a different name. Okay, earlier what we were doing, we were here we are just defining some area, like here the probability of X less than equals to -1, right? Okay, and then so same way we are doing for this probability X is in between -1 to 1, right? So in between -1 to 1, so this can be calculated with some basic probability integration, like you can integrate the normal distribution. So this is the exact thing with the sample proportion. If you are having N equals to 20, so it was bit like very like it was the sample proportion that we were getting is pretty different from the population sample distribution. Okay, if you will start increasing the number of N, now you can see the value is getting converges to 0.683. So this is the same thing we are doing again and again. Okay, so is it done? Okay, so we are now will start with the third lecture. So the third lecture is totally based on the data set. Okay, do you want to discuss this data set also, iris data set? You already if somebody has worked in some basic project in ML, you would have heard about the iris data set. This is the first data set that we generally work on. So do you want to discuss this also? Is anybody here or everybody slept?
Maybe next class. Maybe next class we can continue.
Okay, so may
I think many people have left and few people are there, so this would also get chance.
We can discuss now in next class, that video number 4 and 5.
Okay, I'll just ask because tomorrow I have other session, so maybe.
No, other person whosoever comes on Sunday, so you can pass on this message to him or her.
Okay.
So he or she can start from week number.
Maybe you have tomorrow, I guess, some session in Hindi, I guess. So okay,
No,
I'll just tell
not...
them to go through the third and fourth. So we have covered first and second.
Yeah, fourth and fifth, that additional one, because that is in continuous, sir.
Okay, so third, fourth, fifth. Okay.
Just pass on this message to whosoever is coming. That's it, sir. Okay, sir.
Okay. Okay, then thank you. Good night, everyone.
Okay, sir. Good night.
Thank you very much, sir. Good night.
Thank you, sir. Thank you very much.
Okay.
चली जाते तो वो नहीं आ जाता
Are we stopping for tonight? Sorry, I was away for a couple of minutes.
Okay, so yeah, we'll discuss the rest, I guess, in the next session.
Okay, right. Thank you. Thank you. Don't get me wrong about the questions I was asking. I was trying to ask or find out.
No, not at all. See, no, it's fine, totally fine. Like it was, like it's a like already like this week is pretty confusing. Like this and next week, like what I will read in the next week also, it's a bit confusing. So it's fine.
Yeah, for me, like individual who is in some part of the country, not with the classmates, it's going to be extremely difficult to clarify my doubts. And in Maths 2, actually, in Maths 2, I'm suffering in with linear transformations and everything. It was a bad week last week. So this is the only opportunity I get to actually ask the questions. That's the reason all my questions. Sorry.
You know, you can ask me. You can just mail me also. Whenever you want to ask me, you can ask the doubts. You can just get my like WhatsApp number also. You can text me wherever.
I have your number, Vishal.
Okay, so you can just you have so you called me, I guess, at the Paradox site.
Yes, correct. And after that, we did not really get to actually interact. Would you be able to help with linear transformation as well, or is that something?
I'll help you in that, because in ML most of the time we generally work on that one.
It was my, like it was very pathetic performance on. I did not understand what.
No, that's difficult. Like if somebody like, have you like what are you up to? Like what are you doing now?
I am actually a practicing professional, so I'm an engineer.
Okay.
Engineer in a sense, not exactly. I'm managing a team now, so.
Okay, so maybe there is a gap, right? So that's why.
Yeah. It was really a disappointment to the nth order. So I was just looking for
very
somebody.
Normal. Like it's very like I passed out like last year itself, right, from IIT Madras.
Okay.
So now I can I know there are that if we are having a gap, if we are having gap for 1 year also, we'll be facing issues. And this Maths 2 and Stats 2 is bit like really difficult to understand and to if Stats 2 is like not that difficult if you are just coping with the session, like if you are just attending and then trying to solve, you'll be able to solve. Maths 2 have not went through the syllabus, but if linear algebra is there, that will make you suffer. Linear algebra itself. One topic is.
I didn't expect that I'll be that. Till now, till linear algebra hit, it was okay. It was all right. I was managing everything. It was something around. Quiz 1 also 75. It was okay. It's all right. But linear algebra was a revelation. What all I don't know.
So there is some lecture. If you are not able to grasp, so there are some lectures in the YouTube that you can go through that. I'll just message
YouTube by same professor or.
So there are some animated sort of things.
Okay. That's what you mean. Okay.
So
okay.
will make you, maybe that will help you to grasp more. So I'll just send you the link for the linear algebra part.
Thank you, Vishal. Thank you very much.
Yeah.
And I will definitely trouble you because whatever is going to follow, I'm worried about that. If I am this bad here, next 2 weeks or 1.5 weeks are gone.
I'll tell you, if you are crossing this maths to and stats, so after that you'll not face much issue, because after that maybe that coding part will come and then will be much familiar, I guess. So that is not going to trouble you after this stats and maths. So MLF, machine learning foundation, is maths, bulky maths, but it's all like you already have read. Like it's a mixture of stats to maths to linear algebra with not that difficulty, and then you'll come to the basic coding and all. So it's not that difficult. Only the difficult part is cross the maths to and stats to. After that, I don't think so there is much courses that is heavily like based on maths. So all the other courses are like skill thing, and you have coding and all stuffs are there. So algorithm and all, if you read, there's some basic math behind that. How does it works and all. So those sort of things is not that difficult to understand. That
okay.
That's
I was worried about the basics. I understand these two subjects are laying the foundations.
Yeah,
I'm worried from that perspective.
Person generally face the stats too and maths too. Many people face, but I can guarantee you, if you just go through the sessions and lectures, watch the session, like just go through, solve all the problems. I can guarantee if you are able to solve the graded assignment, practice assignment twice or thrice, I can bet you'll able to solve more than 80% of the problem in the exam. So
maths, this linear algebra, I was not able to get past the activity questions itself. That was what was troubling me.
So some maybe visualization.
Fundamentally, I'm missing something.
So the visualization part you are missing.
Yeah.
How to visualize those linear, how it is getting the linear, what is the basis of this vector, or what are the
exactly.
So maybe those things you are missing. So I'll send you some lecture, you can go through that. Those lectures are like 10 minutes, maybe that will help you. Okay, so and other than that, there are some lectures also, if you want those also I can, or
please.
else you can ask me the doubts. Maybe if I'll be able to clarify, I'll clarify that.
Definitely. Thank you, Vishal. Thank you very much.
Okay.
Thank you. Have a nice evening, and I hope you had your dinner.
No, my food is there.
Okay.
I was about to eat.
All right, go ahead, have your dinner. We can catch up some other day, some other time. Thank you.
Okay.
Thank you. Good night. Bye.
Yeah, thank you. Thanks a lot.
Thank you very much, sir. It was really nice session. Thank you very much, sir. Good night.
Yeah, good night, everyone.